So let me introduce myself again for those who weren't here in this morning or in the afternoon. So my name is Sedef. I'm the Director of Professional Development at Vector Institute. So my team and I, we develop AI training programs for Vector sponsors and partners. And we engage with our sponsors and partners on upskilling towards AI adoption. And prior to this role, I was a senior project manager at Vector, engaged with our sponsors, again, like applied AI project, one of the projects that I'm going to talk about in this presentation. And prior to joining the Vector, I spent my career in building and managing data-intensive R&D project and partnership in the area of AI and ML. And I'm also a researcher in the area of software sustainability design and co-founder of Cross-Corner Alliance on Sustainability Design in Software-Intensive Systems. Okay, so how does this work? All right, that's amazing. So let's look at the agenda of my talk. So first, I'm going to take you to the Vector Institute and talk a little bit of what the Institute does for those who are not familiar with Vector Institute. And then I will visit Vector's recent computer vision project and its focus areas. And after that, I will review some of the project best practices, key lesson learned and conclusions, and future directions. And finally, I will open up the floor for your questions if I have time. All right, so let's get started. Before we dive into the computer vision, so I would like to take you to Vector Institute and talk about a little bit of what the Institute does. So Vector Institute is a not-for-profit institute founded in 2017 as a part of the Pan-Canadian AI strategy. And our mission was driving AI research in Canada with the explicit purpose of fostering economic growth and having a positive impact on life of Canadians. So to achieve this mission, Vector was created as a research institute, which means our researchers focus on world-class research in machine learning, especially deep learning. We also want that research to translate into the real world and be impactful, right? So for this purpose, we work with our industry and government and other institutions to facilitate adoption of AI. So we have over 700 researchers. It includes faculty members, faculty affiliates, researchers, postdocs, students, and so on. And we started something like at 10 or 12. And part of this is in order to create this healthy AI ecosystem in Canada. So we need to ensure that there is a large pool of talent. So those talent will serve to, the research institutions as well as to our industries. So we also work with the universities, try to foster AI master students throughout the scholarship, internships, opportunities, or even in terms of the curriculum design. So here I want to mention about Vector Industry Innovation Team. So how the team work with companies. So Vector's Industry Innovation Team leads industry collaborations. Oh, okay. So Vector Industry Team leads the industry collaborations for driving commercial impact of AI. And basically we had divided into 3 key areas while working with the companies. So first one is technology. The second one is teams. And then the third one is training in terms of the technology. So what we do mostly is we support our partners in the development of their technical capability throughout demonstrations, experiential learning, code, and hands-on experimentation with the latest technologies in AI. So basically, we highlight opportunities for our companies, our sponsors, as well as providing one-to-one access to the researchers, to talent, as we have, and then guide those researchers and the talent. They could guide them throughout the AI technologies and generating insights. So in terms of teams, we provide access to recruitment across the ecosystem of students and researchers, and as well as AI-centric development opportunities. So, and then in terms of training, so we provide different training opportunities to ensure that the participants from the companies or from our partners are kept current with the latest development in this very fast-changing environment. So our industry projects bring industries and researchers together to apply state-of-the-art solutions to a specific industry-related problems. Those problems could be related to one industry, or it could be common across the different industries. So project participants benefit from collaborating with the others, and they could also conduct some experimentations on computing infrastructure that may otherwise be impractical or prohibitively expensive to access. So these are some of the existing project types at Vector. The first one is knowledge transfer projects. So those projects are focused on increasing knowledge and technical expertise of our sponsored participants throughout the experiential learning. And then the second one is use case-based projects. So those projects focus on delivering a technical solutions to an agreed common use case. And then the third one is research-based projects. Those are focusing on producing knowledge by leveraging the state-of-the-art capabilities and resources. And then the last one is a thought leadership project. Those projects are focusing on articulating the expertise on AI topics. So those topics could be technical, those could be strategical or social relevance, and for example, like trustworthy AI or accelerating AI and so on. So let's have a look at the few examples of Vector's applied AI project. The first one, the project that I led like a few years ago, like at the beginning of the pandemic actually. So it's called Dataset Shift Project. So that was developed to the response to the pandemic. And the dataset shift, we look at the dataset shift and its varieties and effective detection strategies and adoption of techniques that we reviewed within the project. And then we had like different use cases, and then those use cases were aligned with the participants' interest. And then we released the project code and project report in our website. If you're interested in, so I highly recommend to go and check the dataset shift project technical report. And then the second example is model-based reinforcement learning. That was actually a very interesting project. So it was started a while ago. It was my first project that I started at Vector. And then since I'm coming from the research background, and then I was focusing on the sustainability, so I had to start with something with the energy efficiency and contribute to the sustainability. So I started this project. So this project aimed to apply model-based reinforcement learning techniques on selected use cases towards reduction of the carbon footprint. So one use case implementation has recently been open sourced by Vector. So we worked with one of our sponsored companies, and then we open sourced the model. So if you're interested, again, so you can check Vector's GitHub for the open source code of the model-based reinforcement learning project. And then the third example is I'm going to talk about today is a project called computer vision, where we apply computer vision techniques to different use cases ranging from manufacturing to traffic incidents, from satellite imagers to healthcare applications. All right, so why computer vision? Why is this important? So we know that the adoption and application of computer vision is growing in many fields, as deep learning-based architecture deliver a greater and more efficient performance on complex image and video-related tasks. So new vision theories and approaches are showing that the potential to drive transformative innovation in many industries, including healthcare, finance and security, transportation and retail, and many more. So from fully autonomous vehicles to automated clinical diagnosis and surgical support systems, so we see vision systems have a major role in technological that are offering an exciting future. So to accelerate these advances, the Vector Institute and its industry sponsors collaborated in this project. And then the project was designed to contribute to innovation to foster greater collaboration between academic researchers as well as the industry practitioners. So additionally, the project aimed to increase the proficiency of the participants at building end-to-end computer vision pipeline and grow ecosystem capacity to derive further advances and application of large-scale computer vision models. So the project have been completed recently, and then the technical report where all the project details and techniques have been given. So again, I encourage you to look at Vector's website for the project report. And then the project repo, where all the use case codes can be found in the Vector's public repo as well. So project focuses on 3 groups. The first one is anomaly and semantic segmentation. The second one is two-stream neural networks, and the last one is transfer learning. So these approaches were applied in the following 5 use cases. The first one is anomaly detection in manufacturing. The second one is semantic segmentation in aerial and road obstacle imagery. And then the third one is automated traffic incident detection with two-stream neural network. And the next one is identifying identifying clinically relevant features of interest in colectomy procedures, which is a gallbladder removal operation. And then the last one is transfer learning for efficient video classification and detection. So now I'm going to give you some of those use cases and examples, and then some of the results that we obtained from those use cases. So in the first area, so we have 2 use cases. One is anomaly detection in manufacturing, where the aim was to explore the use of autoencoders trained on the anomaly detection dataset to optimize anomaly detection on the manufacturing line. The second use case is about semantic segmentation in satellite imagery. And with this use case, the aim was to apply semantic segmentation techniques to satellite imagery for extracting building boundaries. So let's look at the first use case, which is anomaly detection. So we're all familiar with that. The anomaly detection is a very important task in computer vision that is concerned with identifying anonymous images given in the training set of only normal images. So in most cases, having a person manually inspect each component, whether it's anomalous or not. So in this scenario, which is it's not very feasible and time consuming and resource consuming, right? So the recent approaches to anomaly detection employ deep learning models, and then these deep learning models to model the distribution of high dimensional data. So to this end, deep autoencoders have been used and then they are very promising. So in this work, we looked at the 4 types of autoencoders. The first one is a regular autoencoder. The second one is a variational one. The third one is a constraint autoencoder. And then the last one is the context autoencoder. So those models, they have been trained on images on non-defective manufacturing parts. And then the models then tested on MV Tech image data of the real-world parts and assessing each image at the pixel level for anomalies. From the table on the top side, so you can see some of the results. And we can see that the context autoencoder achieves the best performance in this table. And then this strong performance can be explained to the context autoencoder offers a semantically rich representation by learning to paint mask regions of the images in addition to reconstructing them. Okay, so as you can see from the visualization part, the one on the bottom, the context autoencoder further supports the strong quantitative result as we've seen on the table. So there are obviously various limitations. So the team identified some of those limitations. So for example, anomalies are not very well defined or extremely hard to sample. But still, autoencoder-based approaches offer robust solutions to the anomaly segmentation task, especially when compared to supervised methods that are costly and then time-consuming to deploy. So in the second use case, the focus is to explore the state-of-the-art semantic segmentation models. And semantic segmentation plays a very critical role in a broad range of applications, such as autonomous driving, geospatial analysis, for example, building footprint extraction, and medical images segmentation, for example, biomedical marker discovery. And then in this use case, the team aimed at to extract building boundaries from satellite imagery by using semantic segmentation methods. So they used UNet, UNet++, fully convolutional network, and Deep Lab v3 to have, and then those methods, those models are very popular semantic segmentation models. So that's why they choose those models. So in order to benchmark the approach to building a footprint extraction in satellite imagery, the SpaceNet building detection V2 dataset was utilized. And then this dataset consists of high-resolution satellite imagery and corresponding labels that specifically the location of the building footprint. So the dataset includes around 200,000 building labels from across, like a little bit more than 10,000 multispectral satellite images from like different cities. Those cities are like Las Vegas, Paris, Shanghai, and I guess Khartoum is another one. So let's look at the result of this use case. So in total, they explored 6 approaches, and then they benchmarked those 6 approaches on the task of building footprint extraction in the satellite imagery. And then you can see on the top portion of the slides in the table, we have seen like a quantitative analysis. And then the quantitative results shows intersection over union. And then the model that leverages pre-training, for example, fully convolutional network and Deep Lab v3 achieved higher results and required minimal training compared to UNet and UNet++. From the qualitative result on the bottom side, so the methods are able to generate the precise semantic maps in the scene densely populated with the building footprints, for example, the first row and then the last row. And then this work has been published in the Location Intelligence and Knowledge Exchange Conference 2022. And the proceeding, if you would like to interested, you can check out the details of the exploration. So the second focus area is on video, where we have 2 use cases. The first one is related to the traffic incident detection. So we know that the dash cams are very useful tools, and then they become more prevalent in the recent years, acting as a, for example, like a faithful witness to the events surrounding the car or the vehicle. And then being able to detect a risky road behavior is a very important step in the mitigation of the vehicle collision and other road accidents. And for example, drivers demonstrating the reckless driving or near misses may be helped by the additional road training to correct behaviors and prevent future collisions. So the goal of this use case is to correctly identify accidents from dash camera footage. So detection of traffic anomaly dataset have been utilized, and this dataset consists of the videos from different countries under different weather conditions and lightning conditions, because those different conditions are important. And dataset also consists of annotated with temporal, spatial, and categorical. For example, in this frame on the middle side, you can see that the label, the object bounding box is car, is a label, as an object. And then anomaly label is collision with another vehicle moving lateral in the same direction. So those were given in the dataset. So the network architecture that was chosen for this problem was You Only Watch Once, which is YOWO. The YOWO architecture is a special architecture. It's like a very modular architecture designed for action detection in video. And it has 3 main components. The first component is a 3D CNN backbone on the top, and then 2D CNN backbone on the bottom, and then the channel fusion and attention module. While there are many video detection architectures that could have been selected for this problem, but the team chooses this particular architecture because A, it is very efficient and easy to implement, and B, it is a modular, so you can play with those modules. So in order to use these architectures and fit our problem, the team made several changes. So the first architectural modification was to replace the backbone network with once pre-trained or more similar task as traffic anomaly detection, because those backbones are not trained on the traffic anomalies. So they train the 2D Siena backbones on the cityscape data set for semantic segmentation. The second change was made on the 3D backbone. The YOWO only predicts detections and does not have a capability to predict the frame-wise classification. So to solve this issue, an additional classification head was designed to classify the anomaly. So the modified YOWO architecture outputs the two prediction, a bounding box regression classification, and an anomaly classification. So the original lost was used in the YOWO, the one on the top, L box, with an added anomaly classification loss, which is L anomaly. And please, you can check again, this work has been also published, and we also released all the model details and everything in the GitHub. So let's look at the results. So the qualitative examples of the final model in this figures, one on the one side is a success example, another side is the model failures example. And then the ground truth and the prediction are labeled in green and red respectively. I'm not sure if you can see the green and reds here. And this one is pretty obvious. And then the model is capable of detection the multiple weather conditions, and it seems to perform well on common accident types. So as you can see, this one, how I can go back? All right, here. So as you can see here, we have like a snowy, very heavy snow, and then there's another snowy day, and then this might be a rainy day or so. So the model, classifies perfectly for these accident types. And then the model also detects successfully anomaly types involving being hit from the side as class number 3, which is like around 35.9. And then the class ID number 5, which is collision with turning vehicle, which is around like a 70%. This is like a bottom left. And however, there are specific scenarios where the model struggles. More specifically, it has difficulty detecting objects in interest that are far away from the driving vehicle, as well as more rare classes, such as class number 6, as you can see from the table, the collision with pedestrians, for which the accuracy is around 5.9%. And some incident classes have very small number of videos, such as collision with the obstacle in a roadway, and then in this case, the model F-score resulted as 0. So the second use case is from healthcare, and the surgical removal of the gallbladder is one of the most common surgeries. So the complication during the difficult operations can result in the longer recovery and long-term disabilities, even death, right? So the goal of the operation is to remove the gallbladder and not injure the other critical organs surrounded by the gallbladder, for example, liver. The goal of is to save operation and then based on the critical view of safety. So this team goal was to identify clinically relevant features of interest in gallbladder removal procedure using state-of-the-art vision approaches. So there is a relative lack of data set in the healthcare community, as we all know, and then especially data set consists of surgical content. So for the purpose of this use case, publicly available Kocak 8K dataset has been used, and this dataset has like 8,000 frames that have been annotated. So they use two different approaches. One is semantic segmentation. For the semantic segmentation, they use UNet architecture, and for the instant segmentation, they use the Tectron-2 architecture. From the qualitative result, both models have been able to correctly segment most of the important classes. However, it became apparent that not all the classes present in the semantic segmentation result from the UNet would provide clinical clinical value. So they use the instance segmentation and they change the task a little bit. So then the same annotation were used, but the task would focus on binary segmentation, which is go zone or no-go zone. So it was found out that the instance segmentation used in Detectron 2 model provided better result than the semantic segmentation. So as for the conclusion and the key feature considerations, so throughout the project, we learned that the participant gained an expertise on the variety of computer vision techniques and use cases as I just presented. And beyond the project, there are a number of interesting avenues that they can investigate. In terms of general approaches for the future application, some semi-supervised learning models have been found to perform better than supervised learning in certain object detection and in semantic segmentation tasks. And we have seen that the data availability and quality are challenging in most cases, and potentially mitigate the data volume concern is like a auto annotation, which may be especially helpful in the clinical and health setting. In terms of anomaly and semantic segmentation applications in image data, potential future direction could be like techniques such as open set segmentation, and then applying the models to a different data set to evaluate performance and determine additional benchmarks should be further be explored. In terms of the limited amount of the label data, mitigation approach would be the data augmentation techniques to increase the volume of the training data. In terms of the video application, in the traffic incidence detection use case, the future work could be focused on the different and larger data set to prevent overfitting. And then a related direction could be to conduct the additional, the experimentation on the hyperparameter tuning and experimental with the backbone to account for the potential overfitting issues. And then regarding the surgical use case, the number of limitations have been identified. The one limitation is regarding to video quality. So the surgical video data has many challenges because of the quality of the data, especially the lightning. So video captured through a laparoscopic camera that are illuminated using the auxiliary light source for visibility. So another challenge encountered was due to the gelatination of the deformable texture of the organs. So those are, impact the performance as well. Another, of course, limitation is this use case is the annotation. So surgical data is manually labeled by the qualified annotators within the medical field. So this may cause a potential lack of annotators and smaller data set on which the model train on. And then, of course, the model should be generalized to different capture platform and different hospitals use like a different system and so on. And then the last but not least, the quality of the segmentation annotation can significantly vary if there isn't a proper framework provided. So having a system in place to verify and quality checked annotations would give more improved and more consistent result. So with that, I would like to acknowledge all of the project researchers, academic advisors from Vector Institute, University of Toronto, Western University, York University, and the University of British Columbia. And then these are the list of project participants from Vector sponsors and for partners. And they did an amazing job for, completing this project. And finally, I would like to thank all of you to listening to this. And if you are interested, again, please check out the project technical report and the papers that I've just mentioned, as well as the GitHub for the model and implementations. And now I'm happy to take any questions if you have any time.